So folks, the purpose of this review is to review what you've learned in Calculus 2 regarding power series. And I'm going to do as best a review I can in just a few short videos. And then at the very end, there will be some potentially new content that you haven't seen before. So if you're feeling really comfortable in power series and you want to work through this handout on your own, feel free to do so. But do make sure that you watch the last video, which goes through some content that isn't usually highlighted in Calc 2 because it's not as important there, but is vitally important for what we're going to do in our differential equations class. So what I'm going to do in the subsequent videos is review our test for convergence, then we'll give a definition of a power series. Down here we'll give the definition of a power series, and then we'll look at constructing power series for various functions. If you are feeling very rusty, like when I say the word series, you're not quite sure what I mean, please continue on with this video. If you already feel pretty comfortable what a series is, feel free to just jump into the next video. So if you're continuing to watch this video, I'm assuming that you're a little rusty on series. So I want to just remind you of these different terms. So the first thing I want to start with is something called a sequence, which is not a series, but it's just a collection, an ordered sequence. So a sequence may be something like, I don't know, maybe we have 1 over 1 is the first entry in the sequence, and then maybe 1 over 4 is the next entry, and then 1 over 9 is the next entry, and then 1 over 25. And then if there's a pattern that appears relevant, usually what we'll do is we'll put a dot, dot, dot. And so it's this ordered set. And what matters here is that there is an order, so I could talk about the first element in the set or the second element in the set, or I could even change the way I renumber it. A lot of times we'll call this the 0th element, and this is the first, and this is the second. So this is a sequence. And in some cases, what we may be able to do with a sequence is we may be able to give a function that generates it. So I might write something like a sub n is equal to 1 over n squared. And here we've got to be a little bit careful with our numbering, because here above I chose to name this the 0th element, the first element, the second element. But if I want to actually generate the elements of this sequence, I need to input values for n. So in this case, it's important that we say we're going to start this sequence at n equals 1. Otherwise, if I started it at 0 in this case, I'd have an expression that's undefined. And so what I've just illustrated is one of the biggest stumbling blocks of sequences, which has to do with how do you number the elements, because somebody may choose to order a number them one way, and somebody might choose to number them another way. So just to convince yourself that if I give you this sequence right here, b sub n, which is equal to 1 over n plus 1 quantity squared, and we could start it at n equals 0, that here this would start with a 0th element, and it would generate the same list. So these two sequences, even though they look a little bit different, are in fact identical. And the issue has to do with the numbering. Oftentimes if we don't put a terminal value up here, it's implied, but I'm going to go ahead and put infinity up here, meaning that we let n range through the, in this case it would be the counting numbers 1, 2, which never end. But I could stop a sequence by putting some other number here as a terminal value. So folks, we're not going to talk explicitly about sequences all that often in our power series discussion, even though they are the fundamental building blocks of series, and so therefore they're also the fundamental building blocks of power series. So let me just be explicit. This is a sequence. And then I want to talk about an associated series. So for any sequence, we can create a series. And so we're using these two words very differently. We've got sequence and we've got series. And a series is a sum where we're going to add up the various terms of the sequence. So we could take this sequence, a sub n right here, and we could add up between n equals 1 and we could stop at infinity. We could add up all values, so never stopping. So we could give this series right here. So we have a sequence that's associated with a given series. But when you talk about series, it really doesn't make sense to start talking about an infinite series like I did right here. It makes more sense to start with a finite one. So I'd like to start off with this series right here, the series from n equals 1 to 3 of a sub n. So as a reminder, 1 is our starting value for n, 3 is our stopping value. So I could go ahead and give this series, which would be the sum 1 over 1 plus 1 over 2 squared plus 1 over 3 squared. And if I were to add those up, just cheating and using a calculator, I would get 49 over 36. Is that series? By the way, as a decimal approximation, that's approximately 1.361. So I don't think that anything's too complicated at this point. We've just got a sum, but what generates the sum is this underlying sequence, in our case, 1 over n squared. I could continue with this, and we could do something else. I could take the series from n equals 1 to 10 of a sub n, and here I'll just start it out. It's 1 over 1 squared plus 1 over 2 squared plus, I'll put dot dot dot, plus 1 over n squared plus dot dot dot, and we stop at 1 over 10 squared. I really shouldn't put an n here to denote an arbitrary element, since I'm using the counter n, so I need to use some other counter, so maybe I'll put a j. So that's just the jth element in the sum. And so if I ask a computer to crunch that for me, I end up this fraction here, which has a decimal approximation of about 1.549. And we'll go a little further, 1.5498. And bear with me, because I want to do this one more time, but I'll just fill it in. So here I've put up a few more finite sums. I did the sum of the first 1,000 terms of this sequence. So again, what we did was we took this sequence right here, 1 over 1, 1 over 4, 1 over 9, 1 over 25, and I added up the first 1,000 terms, and I got approximately this number here. I did the first 1 million terms, the first 10 million terms, and what you see here is, although there might have been a large jump when I added up between the first 3 and first 10 terms in that approximate value, that jump, the amount that I'm adding each time, gets smaller and smaller. So you can see that because each time I add a new term, I'm adding on a term that's smaller than any of the previous terms. And in fact, if we looked at the limit of this sequence, if we looked at the limit as n goes to infinity of a sub n, that's the limit as n goes to infinity of 1 over n squared. That limit is 0. So each time I'm basically adding on a very small number. And of course in math we've learned that sometimes when you add up small numbers, it continues to get even larger and larger, even though those numbers are small, and other times you might get something called convergence. And in fact, if you were to write out this series right here, which is a finite series, right? If I know what m is, m might be 1,000, or m might be 1,000,000, or n might be 10 million, I can compute that sum, that finite sum, and then we look at the limit as that stop value of our series goes to infinity. And a fun fact is that this series actually converges to a very interesting number, and that's something for maybe some later study. So what we have here is a situation where one way you could look at it is each one of my finite sums gave a new term in a new sequence. So for example, I have the sum when I add up the first 3 values, I got 1.361 approximately. And then when I added up the first 10 values, the first 1,000 values, and this itself generated a new sequence, and this sequence itself, so there's one term of the sequence, there's another term 7 terms later, there's other terms of the sequence, and this sequence itself is converging to a value. And that's what we're interested in, is the situations where when we take the limit as that upper limit of an integration goes to infinity, we actually get a finite value. Okay? So here we can say, shorthand for all this information that we just conveyed, that this series right here is equal to the value pi squared over 6. So folks, that's a real quick review of what you learned about sequences and how they're related to series. And careful folks, I've always found it a little bit confusing. Both those terms sort of sound similar. And in fact, a series, an infinite series, is itself, when we talk about the sum of an infinite series, what we're asking for is for the limit of the sequence of partial sums. So built inside of any series is a sequence. And so there's a lot of room for confusion with these. And while we're not going to get into the nitty-gritty all that often, it's important to understand the differences in terminology. So I hope this video was helpful for those of you that wanted a review of sequences and series, and we will pick up with convergence of series in the next video.